Key benefits of inheritance. Code reusability, avoids redundant code by inheriting attributes and methods from the parent class. Hierarchical classifications, organizes classes into a structured hierarchy, reflecting real-world relationships. Extensibility, child classes can add new features or modify existing behavior. Polymorphism, enables different objects to be treated as if they were of the same type. Types of inheritance in Python. Python supports various types of inheritance. Single inheritance, a child class inherits from only one parent class. Python. Class animal. Def__init__, self, name. Self.name equals name. Def speak, self. Pass. Class dog, animal. Def speak, self. Print, woof. Multiple inheritance, a child class inherits from multiple parent classes. Python. Class flyer. Def fly, self. Print, I can fly. Class swimmer. Def swim, self. Print, I can swim. Class duck, flyer, swimmer. Pass. Multilevel inheritance, a child class inherits from a parent class, which in turn inherits from another parent class. Python. Class animal. Pass. Class mammal, animal. Pass. Class dog, mammal. Pass. Hierarchical inheritance, multiple child classes inherit from a single parent class. Python. Class animal. Pass. Class dog, animal. Pass. Class cat, animal. Pass. Hybrid inheritance, a combination of two or more types of inheritance. Overriding methods. Child classes can override methods inherited from the parent class to provide their own implementation. Python. Class animal. Def speak, self. Print, generic animal sound. Class dog, animal. Def speak, self. Print, woof. Method resolution order, MRO. In multiple inheritance, Python uses MRO to determine the order in which methods are searched for. The C3 linearization algorithm is used for this purpose. Super function. The function is used to access methods of the parent class from a child class. Super. Class parent. Def__init__, self. Print, parent constructor. Class child, parent. Def__init__, self. Super, .__init__. Print, child constructor. Example. Python. Class shape. Def__init__, self, color. Self.color equals color. Def area, self. Pass. Class rectangle, shape. Def__init__, self, length, width, color. Super, .__init__, color. Self.length equals length. Self.width equals width. Def area, self. Return self.length *self.width. Class circle, shape. Def underscore underscore init underscore underscore, self, radius, color. Super, dot underscore underscore init underscore underscore, color. Self dot radius equals radius. Def area, self. Import math. Return math.py asterisk self dot radius asterisk self dot radius. Hashtag create objects. Rect equals rectangle, 5, 4, red. Circle equals circle, 3, blue. Print, rect.area, hashtag output, 20. Print, circle.area, hashtag output, 28.274333882308138. Let's dive deeper into method resolution order, MRO. Method resolution order, MRO, is a crucial concept in Python inheritance, especially when dealing with multiple inheritance. It defines the order in which methods are searched for when an attribute or method is accessed on an instance. Understanding MRO. Python employs the C3 linearization algorithm to determine the MRO of a class. This algorithm ensures that the following principles are adhered to. Consistency. The MRO should be consistent with the intuition that a class should appear before its parents. Linearization. The MRO should be a linear sequence of classes. Inheritance. The MRO should respect the inheritance hierarchy. Example. Python. Class A. Pass. Class B, A. Pass. Class C, A. Pass. Class D, B, C. Pass. Print, d.mrow, hashtag output, class underscore underscore main underscore underscore dot D, class underscore underscore main underscore underscore dot B, class underscore underscore main underscore underscore dot C, class underscore underscore main underscore underscore dot A, class object. As you can see, the MRO for class is. This means that when searching for a method or attribute, Python will first look in class, then, and so on, until it finds a match or reaches the class.dd, b, c, a, object dbcobject. Importance of MRO. Understanding MRO is essential for predicting method resolution. Knowing the MRO helps you determine which method will be called in a given scenario. Avoiding ambiguity. MRO helps prevent conflicts when multiple base classes define the same method. Writing correct code. A clear understanding of MRO is crucial for effective use of inheritance and polymorphism. Diamond problem. The diamond problem is a classic example of the challenges posed by multiple inheritance. It occurs when a class inherits from two base classes that share a common ancestor. MRO helps resolve this issue by providing a consistent order for method lookup. Python. Class A. Def M, self. Print, A.M. Class B, A. Pass. Class C, A. Def M, self. Print, C.M. Class D, B, C. Pass. D equals D. D.M, hashtag output, C.M. In this case, the MRO for is, so the method from class is called .dd, b, c, a, object MC. Let's delve deeper into the diamond problem. Understanding the diamond problem. The diamond problem is a classic challenge in object-oriented programming that arises when a class inherits from two base classes that share a common ancestor. This creates ambiguity about which version of an inherited method to use. Visual representation. A // BC // D. In the above diagram, class inherits from both and, which both inherit from. If has a method and both an override, the question arises, which version of should use, DBCAMBCMMD? Python's approach to the diamond problem. Python's method resolution order, MRO, effectively addresses the diamond problem. The C3 linearization algorithm determines the order in which base classes are searched for attributes and methods. This order ensures that a class always appears before its parents in the MRO. Example: Python class A, def m, self, print a.m, class B, A, def m, self, print b.m, class C, A, def m, self, print c.m, class D, B, C. Pass D equals D. D.m, #output, C.m. In this case, the MRO for is. Therefore, the method from class is called .dd, B, C, A, object MC. Mitigating the diamond problem. While Python's MRO effectively handles the diamond problem in most cases, it's still essential to be aware of potential issues and consider the following. Explicit method calls, used to explicitly call methods from parent classes when necessary. Super. Interface-based design, favor interfaces over inheritance for complex hierarchies. Careful class design, avoid redundant functionality in base classes. Testing thoroughly, rigorously test your code to uncover potential issues related to multiple inheritance. Let's explore polymorphism. Polymorphism is another cornerstone of object-oriented programming, and it works hand in hand with inheritance. It allows objects of different types to be treated as if they were of the same type. Understanding polymorphism. There are two main types of polymorphism. Runtime polymorphism, dynamic polymorphism. This is achieved through method overriding, where a child class provides a specific implementation of a method inherited from a parent class. Python class animal, def speak, self, print, generic animal sound, class dog, animal, def speak, self, print, woof, class cat, animal, def speak, self, print, meow. Animals equals dog, cat. For animal and animals. Animal.speak, #output, woof, meow. Compile time polymorphism, static polymorphism. This is primarily achieved through method overloading, where multiple methods with the same name but different parameters exist within a class. While Python doesn't support method overloading in the traditional sense, you can achieve similar behavior using default arguments or variable length argument lists. Benefits of polymorphism. Code reusability. Polymorphic code can work with objects of different types, making it more flexible. Flexibility. You can write generic code that can handle different object types. Extensibility. New classes can be added without modifying existing code. Polymorphism and inheritance. Polymorphism is closely related to inheritance. By overriding methods in child classes, you create different behaviors for objects of different types, enabling polymorphic behavior. Let's explore practical use cases of inheritance and polymorphism. Inheritance and polymorphism are powerful tools that can be applied in a wide range of real-world scenarios. Let's explore some common use cases. Practical use cases. Inheritance. Shape hierarchy, a base class with derived classes like shape, circle, rectangle, triangle. This allows for common shape properties and methods while providing specific implementations for each shape. Employee hierarchy, a base class with derived classes like This enables shared employee attributes and behaviors while accommodating specific roles. Employee manager developer salesperson. Vehicle hierarchy, a base class with derived classes like. This facilitates common vehicle characteristics and actions, while capturing differences between vehicle types. Vehicle car motorcycle truck. Polymorphism. Shape calculations. A function that calculates the area of a shape can accept any shape object, circle, rectangle, etc., due to polymorphism. Employee management, a system that processes employee salaries can treat all employees polymorphically, calculating pay based on their specific roles. Graphical user interfaces, GUIs. Event handling can use polymorphism to handle different types of events, button clicks, mouse movements, etc., in a unified manner. Deeper dive into polymorphism. Duck typing. Duck typing is a form of dynamic typing where the type of an object is determined by its methods and properties, rather than its explicit type. Python supports duck typing extensively. Example. Def quack, duck. Duck.quack. Class duck. Def quack, self. Print, quack. Class dog. Def quack, self. Print, woof. Duck equals duck. Dog equals dog. Quack, duck, #output, quack. Quack, dog, #output, woof. Even though is not a, it can still be passed to the function because it has a method. Dog duck quack quack. This flexibility is a key aspect of duck typing. Let's delve deeper into duck typing. Duck typing is a powerful concept in Python that promotes flexibility and code reusability. It's closely related to polymorphism, but it offers a more dynamic approach. Key characteristics of duck typing. Focus on behavior. Objects are treated based on their methods and attributes, not their explicit type. Dynamic typing. Type checking is performed at runtime, allowing for more flexibility. Reduced boilerplate. Less code is required compared to statically typed languages. Advantages of duck typing. Code simplicity. Duck typing often leads to cleaner and more concise code. Flexibility. You can work with objects from different libraries or modules as long as they have the required methods. Rapid development. It can speed up development by allowing you to focus on behavior rather than strict typing. Potential drawbacks of duck typing. Runtime errors. If an object doesn't have the expected methods, it can lead to runtime errors. Reduced type safety. While not always a problem, it can make code less predictable in some cases. Best practices for duck typing. Clear documentation. Document expected object interfaces to prevent misunderstandings. Consider type hints. Use type hints for clarity and to aid static type checkers. Gradual typing. Adopt a gradual typing approach, starting with optional type hints and gradually increasing their use. Example, duck typing in action. Def fly, bird. Bird.fly. Class duck. Def fly, self. Print, duck is flying. Class airplane. Def fly, self. Print, airplane is flying. Duck equals duck. Airplane equals airplane. Fly, duck, #output, duck is flying. Fly, airplane, #output, airplane is flying. Let's explore a more complex example of duck typing, data serialization. Duck typing can be particularly powerful when dealing with data structures. Consider a scenario where you need to serialize different types of data to JSON format. Import JSON. Def serialize, data. If #, data, to _JSON. Return data. To _JSON. elif isinstance, data, dict, or isinstance, data, list. Return JSON.dumps, data. Else. Raise type error, F unsupported data type, data. Class user. Def ___ init ___ self, name, age. Self.name equals name. Self.age equals age. Def to _JSON, self. Return JSON.dumps, self ___ dict ___. Hashtag example usage. User equals user, Alice, 30. Data equals key, value. Numbers equals 1, 2, 3. Print, serialize, user. Print, serialize, data. Print, serialize, numbers. In this example, we define a function that can handle different data types. Serialize. The class implements a method for custom serialization. User2_JSON. The function checks for the method and uses it if available. Serialize_JSON. For built-in data structures like end, we use .dict list_json.dumps. For other data types, a is raised. Type error. This demonstrates how duck typing can be used to create flexible and extensible code. Let's delve deeper into a specific use case for duck typing, mocking. Mocking is a testing technique where you replace real objects with simulated objects, mocks, to isolate the unit under test. Duck typing is a natural fit for mocking, as it allows you to create mock objects with the necessary methods and attributes without worrying about their exact type. Example, mocking a database connection. Import Unitist. From unitist.mock import mock. Class database. Def query, self, SQL. Hashtag simulate database query logic. Pass. Class data processor. Def __init self, database. Self.database equals database. Def process _data, self. Result equals self.database.query, select asterisk from users. Hashtag process the result. Class test data processor, unitist.test case. Def test _process _data, self. Mock _db equals mock. Mock _db.query.return _value equals id, 1, name, Alice. Processor equals data processor, mock _db. Processor.process _data. Hashtag assert expected behavior. In this example, we create a mock database object using .unitist.mock.mock. We set the return value of the method to simulate database results.query. We pass the mock database to the .data processor. We can then test the method without actually interacting with a real database. Process _data. This demonstrates how duck typing enables you to create mock objects with the required methods, allowing for effective unit testing. Let's explore another aspect of polymorphism, abstract classes and interfaces. While Python doesn't have explicit interfaces like some other languages, it does support the concept of abstract classes through the module. Abstract classes provide a base for inheritance, defining a common interface that subclasses must implement. ABC. Abstract classes. Define abstract methods using the decorator @abstract method. Cannot be instantiated directly. Ensure that subclasses implement all abstract methods. From ABC import ABC, abstract method. Class shape, ABC. @abstract method. Def area, self. Pass. Class rectangle, shape. def underscore underscore init underscore underscore, self, width, height. Self.width equals width. Self.height equals height. Def area, self. Return self.width asterisk self.height. Hashtag trying to instantiate shape will raise a type error. Hashtag shape equals shape. Interfaces, implicit. Python uses protocols, duck typing, to achieve interface-like behavior. By defining a set of methods, you can create an implicit interface that classes can adhere to. Class flyable. Def fly, self. Pass. Class bird, flyable. Def fly, self. Print, bird is flying. Class airplane, flyable. Def fly, self. Print, airplane is flying. In this example, defines an implicit interface that both and implement .flyable bird airplane. Key differences. Abstract classes can have concrete methods, while interfaces typically only define abstract methods. Abstract classes are enforced by the Python interpreter, while interfaces rely on convention and duck typing. Let's delve deeper into abstract classes and interfaces. Abstract classes versus interfaces, a deeper look. While we've touched on the basics, let's explore the nuances and use cases of abstract classes and interfaces in more detail. Abstract classes. Inheritance. Subclasses inherit both abstract and concrete methods. State can contain instance variables and methods with implementation. Constructors can have constructors. Multiple inheritance, not directly supported in Python, but can be simulated using mixins or other design patterns. Use cases, when you need to provide common implementation details, define a template for subclasses, or enforce a certain structure. Interfaces. Contracts, define a contract of methods without implementation. No state, cannot contain instance variables or methods with implementation. Multiple inheritance, supported in Python. Use cases, when you want to specify a set of behaviors without providing implementation details, or when you need to achieve polymorphism across unrelated classes. When to use which. Use abstract classes when you want to share code among related classes, provide a default implementation, or enforce a specific structure. Use interfaces when you want to define a contract for unrelated classes, support multiple inheritance, or focus on behavior without implementation details. Additional considerations. Python's approach. While Python doesn't have explicit interfaces, the module provides a way to create abstract classes. ABC. Duck typing. Python's dynamic nature often makes explicit interfaces less necessary, as duck typing can achieve similar results. Design patterns. Abstract classes and interfaces are fundamental to many design patterns, such as the factory, adapter, and decorator patterns. Real-world examples of abstract classes and interfaces in Python. Example 1, Shape hierarchy. Problem, create a flexible system to calculate areas of different shapes. Solution. From ABC import ABC, abstract method. Class shape, ABC. Add abstract method. Def area, self. Pass. Class rectangle, shape. Def underscore underscore init underscore underscore, self, width, height. Self.width equals width. Self.height equals height. Def area, self. Return self.width asterisk self.height. Class circle, shape. Def underscore underscore init underscore underscore, self, radius. Self.radius equals radius. Def area, self. Import math. Return math.py *self.radius. *self.radius. Hashtag usage. Shapes equals rectangle, 3, 4, circle, 2. For shape in shapes. Print, shape.area. Here is an abstract base class defining the method, and are concrete subclasses implementing the method. ShapeArea rectangle circle area. Example 2, data storage. Problem, create a system that can store data in different formats, example CSV, JSON, SQL. Solution. From ABC import ABC, abstract method. Class data store, ABC. Add abstract method. Def load, self, path. Pass. Add abstract method. Def save, self, data, path. Pass. Class CSV data store, data store. Hashtag implement load and save methods for CSV. Pass. Class JSON data store, data store. Hashtag implement load and save methods for JSON. Pass. Hashtag usage. CSV_store equals CSV data store. JSON_store equals JSON data store. Hashtag use the appropriate store based on file format. Here is an abstract base class defining the interface for data storage, and are concrete implementations. Data store CSV data store JSON data store. Example 3, logging. Problem, create a flexible logging system that can log to different destinations, example file, console, database. Solution. From ABC import ABC, abstract method. Class logger, ABC. Add abstract method. Def log, self, message. Pass. Class file logger, logger. Hashtag implement logging to file. Pass. Class console logger, logger. Hashtag implement logging to console. Pass. Hashtag usage. File_logger equals file logger. Console_logger equals console logger. Hashtag use the appropriate logger based on requirements. This example demonstrates how abstract classes can be used to define a common interface for different logging implementations. Delving deeper, the shape hierarchy example. Let's explore the shape hierarchy example in more detail, focusing on potential enhancements and design considerations. Adding more complex shapes. We can extend the hierarchy to include more complex shapes like OR. This demonstrates the flexibility of inheritance shape triangle polygon. Import math. Class triangle, shape. Def__init__, self, base, height. Self.base equals base. Self.height equals height. Def area, self. Return 0.5 self.base self.height. Class polygon, shape. Def__init__, self, sides. Self.sides equals sides. Def area, self. Hashtag implement area calculation for polygons. Pass. Incorporating abstract properties. We can introduce abstract properties to capture common attributes of shapes. From ABC import abstract property. Class shape, ABC. Add abstract property. Def number_sides, self. Pass. Add abstract method. Def area, self. Pass. Class triangle, shape. Hashtag. Add property. Def number underscore sites, self. Return 3. Hashtag. Handling irregular shapes. For irregular shapes, we might introduce a pattern to combine simpler shapes composite. Class composite shape, shape. Def underscore underscore init underscore underscore, self, shapes. Self.shapes equals shapes. Def area, self. Return sum, shape.area, for shape in self.shapes. Design considerations. Performance. For performance critical applications, consider using concrete classes for common shapes and abstract classes for generic operations. Flexibility. Balance the need for abstraction with the desire for concrete implementations. Extensibility. Design the hierarchy to accommodate new shape types easily. By exploring these extensions and considerations, we can create a more robust and versatile shape hierarchy. Let's explore a different example, employee hierarchy. Problem: model different employee types within a company. Solution: from ABC import ABC, abstract method. Class employee, ABC. At abstract method. Def calculate underscore salary, self. Pass. Class full-time employee, employee. Def underscore underscore init underscore underscore, self, salary. Self.salary equals salary. Def calculate underscore salary, self. Return self.salary. Class hourly employee, employee. Def underscore underscore init underscore underscore, self, hourly underscore rate, hours underscore worked. Self.hourly underscore rate equals hourly underscore rate. Self.hours underscore worked equals hours underscore worked. Def calculate underscore salary, self. Return self.hourly underscore rate asterisk self.hours underscore worked. Class commission employee, employee. Hashtag, implement salary calculation based on commission. Pass. Analysis. Employee is an abstract base class defining a common interface for salary calculation. Subclasses like, and provide specific implementations. Full-time employee, hourly employee, commission employee. This structure allows for polymorphism when processing payroll or generating reports. Deeper dive, adding more complexity. Benefits: incorporate additional attributes like employee ID, department, and job title. Polymorphism: demonstrate how to use polymorphism for different employee-related operations, example calculate taxes, generate reports. Design patterns: explore how design patterns like the pattern can be used to add benefits or responsibilities to employees dynamically. Decorator. Inheritance versus composition: discuss trade-offs between using inheritance and composition to model employee relationships, example manager-employee. Let's delve deeper into the employee hierarchy example. Adding complexity to the employee hierarchy. Let's expand the employee hierarchy to incorporate more real-world scenarios and design considerations. Introducing employee benefits. Abstract benefit: create an abstract class with methods like n.benefit calculate underscore cost apply underscore benefit. Concrete benefits: implement various benefit types, health insurance, retirement plan, etc., as subclasses. Employee benefit relationship: use composition or aggregation to associate benefits with employees. From ABC import ABC, abstract method. Class benefit, ABC. At abstract method. Def calculate underscore cost, self. Pass. At abstract method. Def apply underscore benefit, self, employee. Pass. Hashtag, Other benefit classes. Class employee. Def __init__ self, benefits equals. Self.benefits equals benefits. Def total _benefits cost, self. Return sum, benefit.calculate _cost, for benefit in self.benefits. Incorporating performance-based compensation. Performance metric. Introduce a class to represent different performance measures, example sales, customer satisfaction, performance metric. Performance-based bonus. Create a class that calculates bonuses based on performance metrics. Performance bonus. Employee performance link. Associate performance metrics with employees and adjust salaries accordingly. Handling employee life cycle. Employee status. Introduce an enum or class, example active, terminated, on _leave, employee status. Lifecycle methods. Implement methods like, and to manage employee life cycle. Hire, terminate, promote, demote. Design patterns. Observer pattern. Use the observer pattern to notify interested parties, example HR, payroll, when employee data changes. Strategy pattern. Employ the strategy pattern for different salary calculation algorithms, example hourly, salaried, commission. By incorporating these elements, we can create a more comprehensive and realistic employee hierarchy model. Let's shift focus to a different domain, e-commerce product hierarchy. Problem: model different product types and their attributes within an e-commerce system. Solution. From ABC import ABC, abstract method. Class product, ABC. Add abstract method. Def calculate _price, self. Pass. Class physical product, product. Def _init__ self, price, weight, dimensions. Self.price equals price. Self.weight equals weight. Self.dimensions equals dimensions. Def calculate _price, self. Return self.price. Class digital product, product. Def _init__ self, price. Self.price equals price. Def calculate _price, self. Return self.price. Class bundle, product. Def _init__ self, products. Self.products equals products. Def calculate _price, self. Return sum, product.calculate _price, for product in self.products. Analysis. Product is an abstract base class defining a common interface for price calculation. Subclasses like, and provide specific implementations. Physical product, digital product bundle. This structure allows for flexible pricing strategies and handling different product types. Potential enhancements. Product categories. Introduce a class to categorize products. Product category. Inventory management. Add attributes and methods for tracking product inventory. Discounts and promotions. Implement different discount strategies, percentage, fixed amount, etc. Product reviews and ratings. Incorporate mechanisms for collecting and analyzing product feedback. Let's delve deeper into the e-commerce product hierarchy. Expanding the product hierarchy. Let's explore some ways to enhance our e-commerce product hierarchy. Introducing product variations. Product variants. Create a class to represent different variations of a product, example size, color, material. Product variant. Option management. Implement options, example size, color, as separate entities to manage product configurations flexibly. Inventory tracking, track inventory levels for each product variant. Implementing product reviews and ratings. Review class, create a class to store customer reviews, including rating, text, and timestamp. Review. Product review relationship, associate reviews with products. Aggregate ratings, calculate average ratings and other relevant metrics. Incorporating product recommendations. Recommendation engine, implement basic recommendation algorithms, example collaborative filtering, content-based, to suggest products to customers. User preferences, store user preferences and purchase history to personalize recommendations. Design considerations. Performance optimization, consider using database indexing and caching for product data retrieval. Scalability, design the hierarchy to accommodate a large number of products and variants efficiently. Data consistency, ensure data integrity when managing product information, inventory, and pricing. By incorporating these enhancements, we can create a more sophisticated and feature-rich e-commerce product hierarchy.